Hello, this is problem number 6 of 2017 IMO competition. An ordered pair x, y of integers is a primitive point if the greatest common divisor of x and y is 1. That is, if two integers x and y are mutually prime. Given a finite set S of primitive points, prove that there exists such homogeneous polynomial of degree n with two variables x and y and integer coefficients that the value of this polynomial in each primitive point in set S equals 1. A polynomial of two variables x and y is called homogeneous polynomial of degree n if the sum of exponents of variables x and y in each non-zero term in this polynomial equals the same positive integer number n. Then the equation in this problem can be written as g of xy equals 1, where g of xy is a homogeneous polynomial of degree n. Everybody who was solving this problem examined this trivial case when set S consists of only one primitive pair, x1, y1. For this case, the statement of this problem immediately follows from the theorem in linear algebra called the Bezout theorem, which states that for any pair of integer numbers x and y, there are two other integer numbers, let's call them a and b, that the value of the homogeneous polynomial of the first degree, ax plus by, equals the greatest common divisor of x and y. And this value is the smallest value of all such polynomials. So, if two integers x1 and y1 are mutually prime, then there is linear function g of xy such that the value of homogeneous polynomial of first degree g of x1 and y1 equals 1. To illustrate this, let's set x1 to 17 and y1 to 12 and walk through the known algorithm of calculating the two coefficients a0 and a1 such that make the value of this polynomial in this primitive point equal to 1. The algorithm is simple. The first two columns are quotient and remainder, and we start from the larger number x1 and divide it by the smaller number y1. So 17 over 12 gives us quotient 1 and remainder 5. Then we divide 12 by 5 and obtain quotient 2, remainder 2. Then divide 5 by 2 and get quotient 2 and remainder 1. Then we divide 2 by 1, get quotient 2 and remainder 0. The remainder 0 stops this process. The next two columns have the value of two coefficients a0 and a1. The first values are 1 and 0, which gives us number 17. The second pair is 0 and 1, which gives us the second number 12. Then we start calculating in each column a0 and a1. We use the previous two numbers and subtract the second number multiplied by the current quotient. So for a0 we subtract 0 times 1 from 1 and get 1. Then for a1 we subtract 1 times 1 from 0 and get minus 1. Then we continue. We subtract 1 times the current quotient 2 from 0 and get minus 2. Then we subtract minus 1 times the current quotient 2 from 1 and obtain number 3. So in this row we get minus 2 and 3 for coefficients a0 and a1. In the next row we subtract minus 2 times the new quotient 2 from 1 and get plus 5. And for a1 we subtract 3 times quotient 2 from minus 1 and get minus 7. This is the final result. Coefficients 5 and minus 7 are the coefficients of the target linear function, which is 5x minus 7y. If we plug in numbers 17 and 12 for x1 and y1, we will get 5 times 17 minus 7 times 12 equals 1. Since the base case is proven, we can try to prove the statement of this problem by induction. The induction assumption is formulated on the screen. Let's assume that for any set of m primitive pairs, there exists a homogeneous polynomial of some positive degree n, such that this polynomial equals 1 in each primitive pair in set S. And we want to prove that for any set of m plus 1 primitive pairs, there is a homogeneous polynomial such that the value of this polynomial in all m plus 1 pairs of set S equals 1. Dan Karman from Israel provided the solution of the induction step. If we have m plus 1 primitive pairs, we can select any subset with m primitive pairs and use the induction assumption that there is a homogeneous polynomial g of xy, whose value is 1 for each pair in this subset. And based on this homogeneous polynomial, we can construct another homogeneous polynomial, f of xy, whose value is also 1 for each pair in the subset with m primitive pairs, and in the remaining pair number m plus 1 as well. The suggested function f of x and y is shown on the screen. It consists of two parts. The second part includes the product indicated by the capital Greek letter pi of the expression yi times x minus xi times y, where index I varies from 1 to m. First of all, we can observe the obvious fact that both parts are homogeneous polynomials of the same degree equal n times capital M. If we plug in any primitive pair from the subset of m pairs in this expression, we see that the first part is 1 regardless of the constant parameter capital M. And the second part equals 0, regardless of the second parameter, capital C. It's because for each pair yi and xi, the product in this expression equals 0. Let's also assume for simplicity that the extra pair, whose index number is m plus 1, is 1, 0, which is a primitive pair. Now let's see what happens with function f of xy if we plug in 1, 0. The value of function f is the value of function g of 1, 0 to the power of capital M minus capital C times the product of all yi. Also, if we plug in 1, 0 to the polynomial g of xy, we obtain that the value of function g of 1, 0 is the first coefficient of this homogeneous polynomial, a0. Then we can write function f of 1, 0 as a0 to the capital M minus capital C times the product of all yi. In a special case, when a0 equals 1, we can set capital M to 1 and capital C to 0. In other words, the given homogeneous function g of xy also works for the pair 1, 0. Its value in it is also 1. On the other hand, if we plug in any pair xi, yi into function g of xy, whose value, as we know, is 1 with these arguments, then we can write the modular equality that this value is equivalent to the same first coefficient a0 times xi to the n modulo yi. This is because all other terms of polynomial g are the multiples of yi. This modular equality can be rewritten as a0 times xi to the n equals some integer number k times yi plus 1. From this, it immediately follows that the first coefficient a0 is mutually prime with yi. Because if you assume that ai has at least one common divisor with yi, then that divisor could be factored, and we would get that that factor times some integer number equals 1, which is, of course, impossible. This is the key result that enables us to use the Euler's-Fermat theorem, which uses the Euler-tangent function phi. If we set capital M to some multiple of Euler's function phi of the product of all yi, and since we know that a0 is mutually prime with the product of all yi, we can write a0 to the capital M minus capital C times the product of all yi equals 1, which proves the statement of this problem for the case when the extra pair number m plus 1 is 1, 0. We have shown how to construct the target homogeneous polynomial for set S of m plus 1 primitive pairs if one of m plus 1 pairs is the trivial pair 1 and 0. If, however, set S of m plus 1 primitive pairs does not have the pair 1 and 0, then let's use the polynomial g of x and y for any subset of set S that has m primitive pairs. And for the remaining pair, which has sequential number m plus 1, we'll find two integer numbers, t and s, such that t times x m plus 1 plus s times y m plus 1 equals 1. We know that such integer numbers t and s exist. It's the statement of the Bézout lemma. Then let's use the matrix of linear transformation with two rows. The first row consists of numbers t and s, and the second row consists of numbers minus ym plus 1 and xm plus 1. We see that if we use this matrix to convert our given pair xm plus 1 and ym plus 1, the result of this matrix multiplication is the pair 1 and 0. It's a known fact in linear algebra that such matrix with two rows and two columns is invertible if its determinant is not equal to 0. The determinant of this matrix is t times x m plus 1, it's the first diagonal, minus y m plus 1 times s, it's the second diagonal. This determinant is equal to 1, which is not 0. So this transformation establishes one-to-one correspondence between all pairs xy and all pairs uv. And for the matrix of this transformation, there exists a unique inverted matrix that converts all pairs uv back to their corresponding counterparts, pairs x and y. Now we need to do the substitution of variables x and y in our homogeneous polynomial g of x and y and convert it to g1 of u and v. Then construct the target homogeneous polynomial function f1 of u and v and use the inverted transformation to express the target function f1 of u and v in the original variables x and y, and we are done. In the first example, the first pair is 17, 12, and the second pair is 1, 0. Based on the first pair, we identify the homogeneous polynomial g of xy equals 5x minus 7y, so that g of x1, y1 equals 1. Then we construct the target polynomial f using the formula with two parameters, capital M and capital C, to be determined. We know that this function f equals 1 in the first pair, x1, y1, regardless of the values of M and C. and the value of f of 1, 0 equals 5 to the capital M minus capital C times 12. Then we calculate the Euler's tangent function phi of argument 12. We use the simple formula that is based on its prime factorization, and we obtain the value of function phi equals 4. The target function f in the arguments 1, 0 equals 5 to the 4 minus 52 times 12, which equals 1. And the general formula for the homogeneous polynomial f of xy is 5x minus 7y to the 4 minus 52 times x cubed times 12x minus 17 times y. It can be easily verified that this homogeneous polynomial of degree 4 equals 1 in both given primitive pairs. In the second example, set S consists of two primitive pairs, 3 and 2, and 2 and 5. The homogeneous polynomial g of xy based on the first pair is x minus y, so that g of x1, y1 equals 1. Then we identify the invertible linear transformation that converts the second pair, 2, 5, into the trivial pair 1, 0 in the new coordinates u and v. Such transformation is called isomorphism. The matrix of the linear transformation that transforms point 2, 5 in xy coordinates to point 1, 0 in uv coordinates is the 2 by 2 matrix, in which the first row is minus 2, 1, and the second row is minus 5, 2. The inverted matrix that transforms all the pairs in u and v coordinates back to x and y coordinates consists of two rows, 2 minus 1 and 5 minus 2. If we multiply these two matrices, we obtain the identity matrix 1, 0, 0, 1. If we make substitution of variables x and y with their conversion formulas in terms of u and v, we will obtain the new homogeneous polynomial g1 of u and v, which is minus 3u plus v. The linear transformation in the upper right corner of the screen converts the second pair, 2, 5, into 1, 0, and the same transformation converts the first pair, 3, 2, to minus 4, minus 11 in coordinates u and v. v1 coordinate of the first pair equals minus 11. Since 11 is a prime number, the value of function phi of 11 is simply 11 minus 1 by definition of Euler's tangent function phi. So the value of the parameter capital M equals 10, and we can calculate that the value of the second parameter capital C is minus 5,368. Since g1 function of uv equals minus 3u plus v, the first coefficient a0 equals minus 3. So f1 polynomial in coordinates u and v is written with these two values of parameters capital M and capital C. And the final step is to make a substitution of variables u and v using the linear transformation formulas shown in the upper right corner of the screen in polynomial f1 to write it as the required version of this function f of xy. This homogeneous polynomial f of xy is written at the bottom of the screen. It's easy to verify that if we plug in the x1 and y1 coordinates 3 and 2 into this function, the value of the function is 1. And so it is if we plug in the coordinates of the second pair. This completes the analysis in these two examples.